Hiya! So in this video, we're going to be continuing looking at the definition of a rotation in 3 dimensions. So let's recall kind of what this kind of looks like, how the setup was, and then we're going to look at this in a more geometric light. So here I started off with some orthonormal basis B, where we have n hat. Remember, this is the normalized version of n, given by formula 1.27. Then I have 2 other vectors, and I'm going to look at a rotation around some axis L. Remember, what this looks like is some tire with a point, and I'm rotating in kind of 2 dimensions, which gives me these formulas for this rotation, right? So I'm specifying Ln is going to be my axis. I keep the axis as is, and I rotate everything else. So let's break down this definition and see kind of what's happening. So the first thing is that precisely that all the vectors on this line stay exactly where they are, right? So on the axis of rotation, everything's there, stays exactly where they are. And that's because we can just take the lambda of a vector, pull it outside the linear operator, and then operating on this n gives us exactly where it is. So this is identical to n in a linear algebra term, because the scalar multiples of n doesn't really do anything. So what's another way of seeing this? If we look at linear algebra, what this is basically saying is this is equivalent to n being an eigenvector of P with eigenvalue lambda. Eigenvalue 1. Yeah, eigenvalue 1. Why is that? Well, what is this, right? So this we can consider as the matrix, or we can just look at the linear operator, right? And we're just multiplying, so this is giving us kind of the same format as we saw before, right? So we have m times n gives us precisely lambda n. So this is almost the same. So you can kind of see it has a very similar feel to it. If I look at 1.29 and 1.3, so I look at these other 2 equations, as we saw, this is exactly the f and g. If I just look at those 2 elements, in other words, I just look at this 2-dimensional subspace, that is precisely going to give us a normal rotation. So it gives us a normal 2-dimensional rotation, which we saw by this cosine phi minus sine phi, etc. And since this basis is orthonormal, the plane is orthogonal to n. And so this entire plane, kind of what I was drawing, is moving around L of n, around the axis L of n. Now what we can do is, if we look at the trace, so if I look at this matrix, I look at the trace, and remembering that the trace doesn't change, I have 1 plus cosine phi plus cosine phi. So the trace of a linear operator over the rotation is always going to be the same. So this trace doesn't change for a rotation, where phi is going to be the angle. And here, just remember that the trace of P doesn't depend on the choice of basis. So it doesn't matter what basis we started off from, it's going to be the same. Another thing is to kind of notice that cosine of phi and minus cosine of phi determine the angle of rotation up to sine, right? So since they're equal to one another, rotating one direction or rotating another direction, it doesn't really change the trace, right? Like if I rotate 50 degrees this way or 50 degrees this way, the trace is going to be the same, right? It's really the sign that's going to be thinking. So in other words, this trace formula only determines the angle up to sine. So if I'm given the trace, I don't know if I went 50 degrees this way, 50 degrees that way. I have zero idea. And now we can actually look at Euler's rotation theorem. And yeah, so what is Euler's rotation theorem? So what we can do is first we'll notice that P is orthogonal and preserves the orientation. So this you can kind of check if you want. And Euler's rotation theorem is basically saying the opposite is true as well. In other words, if I have, we'll highlight this. If any orientation preserving orthogonal operator, right? So it preserves orientation and it's orthogonal, then it must be a rotation. So rotations are precisely the orthogonal preserving operators. So in other words, in more explicit details, we let P be an orientation preserving orthogonal operator. Then P is a rotation around an axis L. We don't know what it is, but we just know there exists some axis L by the angle phi. And more explicitly, the axis L is the one-dimensional space of eigenvectors of P with eigenvalue 1. So we kind of saw this last time. So basically the eigenvector whose eigenvalue is 1 is precisely this axis. And moreover, we know that the phi is determined up to sign using the trace of the linear operator. So it gives us a lot of information in the sense that once we have the trace of the linear operator and we have its eigenvector, we know the axis and we know by how many degrees it rotated, but we might not know which direction it rotated. We're gonna prove this later on. But I'm gonna stop here. And we're gonna look at an example in the next video and then maybe prove this depending on how long the example takes. So yeah. So I will leave you here and I'll see you in the next video for an example. Peace.